Hello, and welcome to this next video on multiplying a monomial by a polynomial, a binomial, or a trinomial. Okay, so now, first we looked at multiplying simple monomials. Now we're going to look at multiplying monomials when we have to deal with exponent rules. Okay, so we're going to talk about exponent rules as they involve distribution. Okay, so some important things to remember. One, order of operations still apply. Okay, so don't forget that. Two, we're going to use the distributive property that we just learned. And three, we're going to use all of those exponent rules, those 7 rules that we learned before. Okay, so the first one was 0. The second one was identity, negative, product of a power, power of a product, quotient of a power, and power of a quotient. So we're going to be using those rules interchangeably. So all those rules still apply, so don't forget anything that you've already learned. Okay, so we're going to start out by looking at this key. Okay, so maybe you've used algebra tiles before and maybe you haven't. So if you haven't, then of course the blue square tile, okay, it's supposed to be a square, maybe a little distorted on your screen, represents x squared. The long green tile, or the long green bar, represents x, and then the small little yellow 1 represents a positive 1. Now, at the bottom, you see some all red tile. So any red tile represents negative. So the same size square big blue tile represents a negative x squared. The bar, the long red bar, represents a negative x. And then, of course, the small red square represents a negative 1. So we're going to be using these. So let's do a picture activity first. Okay, well, we can see this line with the tiles around them represents our algebra tile mat. So it tells us to write the product or variable to represent each colored tile. Okay, well, we know that the first colored tile represents an x. And we know that the other green colored tile represents an x, and each one of the yellows represents a 1 according to our key. Okay, so we're going to write the number or variable to represent each colored tile. We did that, and so you can see that some little columns or some lines appear, okay, that trace out our tiles. And so what we're going to do now is use these lines. So remember we had an x here, a 1, a 1, and a 1 to find the product. So what we're going to do is multiply each row and column represented, and we're going to put the product of the row and the column into each box. So x times x is going to give us x squared. And so we're going to replace that with the tile that should be there. X times 1 would give us x, and then x times 1 again would give us an x, and then x times 1 again would give us an x. So what tiles do you think should be there? Okay, well, if you guessed that this one should be x squared, that's correct. This one should be x, and this one should be x, and this one should be x. So notice that we had x here, 1, 1, 1. So the expression that we got up here along the top bar was x plus, we have 3 1s, so that would be 3. And over here, the expression was x. Well, what happened was we multiplied a row by a column. So we said x times x would give us x squared, and we said x times 1 would give us x times 1, x times 1, x. Well, what did we just do? Well, if I do that again, I'm going to say x times x plus 3. Well, let's use distributive property for this, okay? So I'm going to multiply the x times the x and the x times the 3, and that's going to give me x squared plus 3x. Well, isn't that the same thing of what I would get if I actually wrote out the expression of the product that I get from these tiles? Let's see. I have 1x squared tile plus 3x tiles. Same. So x squared plus 3x is what I get from the product. So all I do is add up the result of each product, x squared plus 3x, and I combine any like terms. Well, here in this case, I don't have any like terms, so I'm good, and I can move on to the next problem. All right, multiplying monomials and binomials. Okay, an interior decorator is expanding the length of a square room to be 2 feet longer than its width. Well, what is the area of the new room? Okay, so we said the room is a square room, right? So the length of a square room, they're expanding it. So the original room represents this blue area here, and then the extension or the expansion is this little purple area here. So if I wanted to give the blue area, the original area, dimensions, we know that a square is side, or you can use x if you want to, right? So each side is the same. All four sides are the same. Well, they're going to expand it by 2 feet, okay? So, oops, I went backwards somehow. Let me go forward again. So, if I wanted to find the area of the square, the area of this square is equal to s times s. So side times side, which is side squared, right? And then I have 2. Well, what is if I look at this rectangle, I know that this width is 2, but what about this one? What is it? Oh yeah, if I look over here, these are the same length. From here to here is the same as from here to here, right? So I can call this s. So the area here would be 2 times s. Okay, so I end up with the area of the total, the area of the old room, right? The area of the old plus the area of the expansion. The area of the old, we said, was s squared, and the area of the expanded area was 2s, so plus 2s. Well, let's see what that looks like if I used distributive property. So if I have a square here and I'm adding 2 feet, that's s plus 2, and if this dimension is s, then this dimension could be possibly my length or width, whichever one you want to call it, right? And so I would multiply s times s plus 2 to get the whole area of the room after it's been expanded. So that's going to be s times s plus 2. And so I get s times s and s times 2, which gives me s squared plus 2s. Voila, I got the same thing. S squared plus 2s and s squared plus 2s. Let's try another problem. All right, that was just the answer. I went a little ahead of myself. I already explained it. Okay, let's try this one. We have multiplying a polynomial by a monomial. All right, so this time we have an area of a whole block that's separated into 3 parts. So I don't know the area of the whole thing, right? But I do know the area of each individual piece. So the area of this piece plus this piece plus this piece would give me what I needed. So let's find the area of each individual piece. All right, well, if I find the area of 2x times 12x squared, that's going to give me 24. X times x is x squared. And then if I do the area of 2x and 3x squared, that will give me the area of this piece. And so that's going to be 6x cubed. And then if I want the area of this small box here, well, it's going to be 2x, this dimension, and then this dimension is 8. So that's going to give me 16x, right? And so if I if I add up all the pieces together, the total area, the area of all 3, so area total is 24x squared plus 6x cubed plus 16x. And my final answer should be 6x cubed plus 24x squared plus 16x. And if you ask why, it's because this is standard form. Remember that we have to put our final answer in standard form. Okay, so now let's look at this from a different perspective. Okay, let's look at it if we're going to use distribution. Okay, so let's say that instead of finding the area of each box, that I decided to write this as an expression. So 12x squared plus 12x squared plus 3x squared plus 8. Okay, so since those are all positive, that means that they're all being added. So what I want to do is I want to find the length of the whole box first, and then I'm going to multiply that by the width, which we're calling 2x. So basically what I would do is distribute. So if I were to rewrite that as an expression, I would have 2x times 12x plus 3x squared plus 8. So 2x times 12x squared plus times 12x plus 3x squared plus 8. So if I distribute that as I would in a normal monomial times a trinomial, then I would end up with 24x squared plus 6x squared plus 16x. Sorry, 6x cubed. And so when I rearrange that again in standard form, it comes out as 6x cubed plus 24x squared plus 16x, just like the way that I did it after I added up each area. Okay, so it comes out to be the same. All right, now let's go to the next problem. Okay, so multiplying monomials, polynomials, and monomials recap. So what we learned is that we distribute just like we do. However, we may have some exponent rules to apply. So for instance here, if I have 5x times 3x, and I also have 5x times 2, well, I have to multiply the coefficients just like I would if I were just multiplying two exponents. So this would be the product of power rule. So this will become 15, and then now x to the 1, I add the exponents, and so that's x squared, plus 5 times 2 is 10, and since I only have one x there, it's going to be 15x squared plus 10. Let's try another one. Okay, we have negative 4a times 5a squared minus 2a plus 6. Okay, so I definitely have some exponent rules to apply here. And in this case, negative 4 times 5 comes out to be 20. So I'm still distributing, plus I'm using exponent rules. 20a, that will be cubed because there's a 1 on a. And then this is going to be plus, so integer rules also. Negative, negative becomes positive 8. And then a squared, because there's a power exponent of 1 on each of those a's. And then minus negative 4 times 6 is 24. And I'm left with a, because we only have one a there. Okay, let's try another one. Let's try negative g times negative gh. So that's going to give me a positive g squared h when I distribute. And then when I distribute negative g to 2, it's going to be minus 2g squared. And then when I distribute, again, that's going to be positive 5g. Okay? And if you're worried about standard form for this one, of course, there's an exponent of 2 on g and 1 on h, so that's a degree of 3. There's a exponent of 2 on g, so that's a degree of 2, and there's a 1 on, there's a 2 on g squared, and there's a 1 on g, so that's a degree of 1, so it is in standard form from highest degree to lowest degree. Okay, so this is just talking about the degrees, so you don't really need to worry about that. Now let's go on. Let me erase all ink on the slide so that I'll have enough time. So if you need to pause the video to copy, you can, but I'm going to erase all the ink so that I can go on to the next problem. Okay, so now we have a more complicated one. In this case, I'm multiplying a monomial times a binomial first, and then I'm adding two binomials. So the first thing that I have to do is to distribute, because I don't want you to get confused, so I'm throwing some of that in, because we need to know the difference when we're multiplying monomials and polynomials and when we're adding polynomials. All right, so I have d squared times 6 first, and so that's going to be 6d squared minus d squared times d, which will be d to the third power. And I can take that out of brackets, or I can leave it in for now, but it's just like having a 1 there, so it's fine for now. And next I have 3d minus 4 in brackets. So since everything is positive, I can just remove it and then combine any like terms that I have. So 6d squared minus d cubed plus 3d minus 4. And as I can see, I don't have any like terms there, so everything just stays as it is, except I need to rearrange the 6d squared and minus d to the third, because d to the third actually has a higher degree or a higher exponent. So d to the third, so negative d to the third plus 6d squared plus 3d minus 4. And so now everything is in standard form. Okay, let's try another problem. And I'm going to have to erase my ink again. So let's erase all ink on the slide and let's try this problem. So I have 2h, a little more complicated, times 4h cubed I plus 2h times 6h. And then I have another monomial times a binomial. So I times I to the fourth and negative I times negative 1. So I need to distribute first, and then after I distribute, then I can combine any like terms if I have any. So in this case, I would end up with 2 times 4 is 8, and then h to the first times h to the third will become h to the fourth, I, plus, and now that's going to be 2 times 12, so that's going to be 12, and that's h to the second power. And then that's going to be minus, over here, it's like having plus negative I, so negative I to the first times I to the fourth will become minus I to the fifth, and then negative I to the first times negative 1 will become a positive I. So I'm left with just positive I. And as I can see, I don't have any terms that are alike, so there is nothing to combine in this case. So I am done. Okay. So one more for practice. Let's see if you can do this one. So pause the video and see if you can work this one out. You can use this method or you can use distributive property. But either way, you'll get good. You'll get better at these by more practice. So let's pause the video. Okay, so first you need to determine what each tile represents. So if you determine that this one is x, this tile is negative x, so negative x, I'm going to write it off to the side because it's red on red. Okay, we have a 1, and then these are also 1s. So up here I have x plus 3, and over here I have a negative x plus 2. All right, so x, 1, 1, 1, negative x, 1, and 1. So what I want to do is I should multiply each row by each column again. So here I have negative x times x will give me negative x squared, and negative x times 1 will give me a negative x. So if I draw my squares in, and then negative x times 1 is negative x again, negative x, and then now let's separate these. So for here I get 1 times x, which is x, 1 times x is x, and then 1 times 1, I have 1 times 1 all the way for 3, so that's 1, 1, 1, and 1 times 1 again, 3 times is 1, 1, 1. So the expression that I end up with is negative x squared. Well, how many x's do I have? 1, 2, 3 negative x's, so minus 3x. And then I have 2 positive x's, so that's plus 2x. And then I have 1, 2, 3, 4, 5, 6 1s. And so what happens is I can combine any like terms here, and these like terms, negative x plus 2x becomes negative x. I'm sorry, negative 3x plus 2x becomes negative x. So I have negative x squared minus x plus 6. And if you don't want to skip this step here, you actually could just cancel out 0 pairs. So every x and negative x will cancel out, and every x and negative x will cancel out. So that leaves you with 1 negative x. Okay, so that's just a visual way to check. So let's see if we're right on the next slide. Let's see what our squares they put in. All right, so it looks like we are right. Negative x squared plus, minus 3x. Well, plus 2x minus 3x, and then plus 6. So negative x squared minus x plus 6. Remember, we have to combine those like terms.